Today we study photon propagator. Let us recall the electromagnetic interactions Lagrangian density function. That is, for the free particle case, it is 1/4 f mu nu f mu nu, and if there is any interaction, it appears to be minus j dot a. And this contribution is independent of gauge, so it is a gauge invariant expression. But a mu is 4-vector potential, and its momentum space expression is a mu is proportional to epsilon mu, that is polarization vector, and remaining piece is the same as the case for example, it is k e to the minus I k dot x, something like that. So integration over this momentum, then it is a wave function at position x. So, as we know, it is the wave function of the photon is orthogonal to the momentum. Okay? It is two-dimensional object. In 3 dimensions, it is the polarization is orthogonal to the whole momentum. And if you choose the gauge, for example, its zeroth component of polarization vector vanishes, then it is just and if it is moving along the z direction, the wave function is just a 2-dimensional. So we begin with the 4-dimensional object, and because of this transverse condition, it kills 1 degree of freedom, and then it becomes a 3-dimensional object. But gauge condition kills another contribution, so finally it becomes a 2-dimensional object. Okay. So in any case, divergence A, it can be treated to be 0. So in this gauge, divergence A is 0. So why don't we copy the method that has been used for the constraint equation? In the classical mechanics, if there is a constraint, we just introduce Lagrange's undetermined multiplier, and usually we use that lambda to find the constraint force so that an object is along the constraint equation. So this lambda, for simplicity, we have chosen this lambda to be 1 over 2 alpha with negative sign. And if I want to impose this constraint condition, it is good to use the same dimensional object. This Lagrangian has 2 gauge field. A mu appears twice and derivative appears twice. So it's better to introduce a divergence A squared, so that the dimension of this term is the same as the remaining piece. So why don't we make use of this relation and find the propagator? So we call this additional piece that actually vanishes, but for the time being, until we obtain the Euler-Lagrange equation, we do not say it is vanishing. But after deriving the equation, we can impose that divergence A vanishes. Okay, Euler-Lagrange equation is written like that, and we have introduced this term, so let us rederive everything. Kinetic term depends on the derivative of the gauge field, and we already know that if I take the derivative, there are 4 possibilities. Here there are 2 terms, and they are anti-symmetric. That overall final result is just minus f mu nu. I assume everybody knows about that. And second piece is, where is it? Okay, I'd like to compute this contribution. This one has derivative, So this one is copied in here without the factor 1 over 2 minus 1 over 2 alpha. If I put it here with the alpha and beta with different notation, then non-vanishing contribution is if this guy means this guy means this. Okay? The first one is mu, alpha, they are the same, nu, alpha, they are the same. You know, if the derivative is written below, then the covariant and contravariant, they are flipped. So mu is going up and nu is going up. But in the numerator, everything is the same. This alpha is here, that alpha is here, beta is here, this beta is here. But after taking the derivative, this contribution has divergence A contribution. If this guy take the derivative on the right factor, then left factor remains. If I compute this, alpha will be contracted. It is just a g mu nu, and this guy is also g mu nu. So I have factor of 2 g mu nu divergence A. Right. So this term, I have two contributions, minus f mu and the 2 times g mu nu divergence A, but I have multiplied minus 1 over 2 alpha in here. Then this guy, factor of 2 cancels, it becomes minus 1 over alpha. Okay? And then take the derivative, and what is the source term? A new derivative is applied only in here, and minus sign and minus sign, they become positive, and the J nu current is up here. So if I combine these two things and move this to the right hand side and flip the left and right, then the final result is around mu f mu nu plus 1 over alpha around nu and divergence A equals current J nu. Let us expand this field strength tensor, that is round mu A nu subtracted by round nu A mu. So this is the whole expression. Let's see, there is divergence A, divergence A. So these two terms can be combined. So if we combine these two terms in a single term, it is 1 over alpha, minus 1, round nu with A nu down. Okay? But note that I have replaced the nu and mu. So the equation of motion is constructed. Now we find that the equation of motion is depending on gauge. You know, right hand side is independent of gauge, but this wave function itself has a gauge dependence. Perhaps that this contribution cancels the gauge dependence. Okay. If I write down the equation of motion, next step is replace the current by delta function, right? And in the case of vector case, we have some matrix that connects the vector component. So I have the same operator, but nu is contracted with a propagator who has the two indices. One is contracted to the left hand side, the right hand side, this vector index will be contracted to another function. So that if I multiply a vector, 4 vector object to both sides, then g mu nu give this vector index mu to the right hand side. Next step is to find my propagator for this equation of motion. let me just guess the form of gauge invariant form, the gauge dependent form of that Photon propagator. We know it is massless particle, so denominator must have a correct pole. So p squared plus I epsilon must appear in the denominator, and it has oscillating factor e to the minus ip dot x, and the numerator is our problem. This guy has vector indices nu and alpha, and we have rank 2 tensor, but you know there's only the only available vector is p. So if I want to make a rank 2 tensor, the only possibility is g mu nu metric tensor and p mu p nu. There's nothing else to introduce. So the most general form is A g nu alpha and B p nu p alpha. To simplify, to make these A and B dimensionless, I want to divide p squared in advance. So that doesn't change anything. So this trial solution, if there is solution, this trial solution must work. So let us substitute this trial solution to the original equation. Then the same operator appears here, and that operator acts only on the exponential factor that has x dependence. So if I take the derivative twice, then I have minus p squared, right? Minus p squared. So I have pulled out p squared out and kept minus sign in here. And double derivative also gives a negative sign, so I have flipped the order, 1 minus 1 over alpha. So p mu, p nu divided by p squared. Okay, let us substitute this result in original equation. Then this is the vector expression. And what's that? What's that? This one I have to substitute in here. I have p squared in the denominator, p squared plus I epsilon in the denominator. But when I take the derivative to this exponential function, what I have was over a factor p squared that cancels the denominator. Still there is exponential factor. Alright, I'd like to expand this. If I expand, minus a g mu alpha, and crossing term minus b p nu becomes p mu and p alpha, right? Divided by p squared. And this crossing term is a times 1 minus 1 over alpha p mu nu, so it becomes alpha p mu p alpha divided by p squared. And last term is this one and this one. So I have over factor b, another over factor 1 minus 1 over alpha, and if I contract this p nu and p nu, it becomes p squared. We have double p squared, and one of double p squared disappear, and remaining pieces p mu p alpha divided by p squared and exponential factor. We know our requirement is that the right hand side is a g mu alpha delta function. So this factor must be expressed in terms of that. That means this p dependence cancel exactly, and p independent factor is just g mu alpha. Then remaining piece over factor, this integral can go inside, and then it becomes delta function, right? So first, minus a must be 1. that means A is minus 1. Okay, A is determined. If A is minus 1, then I have minus 1 over alpha minus B. They are the same in P mu P alpha P squared. These two terms must cancel. If I combine them, minus B is here, plus B, 1 minus 1 over alpha equals 0. They must disappear. If I simplify, if I combine these two, 1 and minus B cancel, and I have minus 1 over alpha multiplied by B, and this guy can be moved to the right hand side, that is 1 minus 1 over alpha. If I multiply minus alpha to both sides, then B is 1 minus alpha. So, A is minus 1 and B is 1 minus alpha. We indeed found the solution. So therefore, the Photon propagator for the photon with this general gauge fixing term is integration over the four-dimensional momentum with the numerator minus g mu nu plus 1 minus alpha p mu p nu divided by p squared plus I epsilon multiplied by exponential minus I p dot x. Okay, it is so general. If I vary alpha in various value, it is also true. So this one may, the gauge dependence of the left hand side cancel exactly to make it be the same as the right hand side, which is independent of gauge. Okay, let's see if there is any possibility of any gauge dependence on the right hand side, but let us postpone the discussion of the details. But anyway, regardless of any value of alpha, we have propagator. Okay. In the previous class, we have Lorentz gauge. The result is obtained when alpha is equal to 1. Then it disappears. Although this guy is ill-defined as alpha goes to 0, but we can still take the limit alpha goes to 0. In that case, the last term becomes infinite, but infinite. However, in that case, this one becomes just 1. Okay? And if this term vanishes, the alpha goes to infinity, what happens? Alpha goes to infinity, this term goes to infinity. Okay. That's it.